In addition to particle size distribution, the surface area measurements can be very useful. The BET method, based on molecular absorption, say of nitrogen or helium, that's a way to be able to measure for a monolayer absorbed what is the overall surface area. Another attribute that can be measured as density, but there are many different forms of density. On the top is a technique called tap density. At the bottom is called apparent density or bulk density. So in terms of packing density, you have a mass of powder that's occupied in a given volume. In apparent density, which is in the bottom case, it's same as bulk density. It is the amount of powder, loosely packed powder in a known volume in the cylinder. In terms of tap density, that by vibration, you end up starting with a higher volume of powder, which then settles in and packs down to a limiting value. Okay. Compaction density actually pushes the powder down, and depending upon the pressure. And finally, picnometer density gives you the theoretical density, and helium gas is typically used to measure the overall volume of that is known. Put a known weight over there, be able to account for the volume of pores that exist between the particles, and then come up with the density of the powders themselves. If there's closed porosity within the powders, that will show up in the picnometer density values that will be lower than the measured density for a fully dense piece of material. We have looked at various powders in 3D printing operations. You can either just sinter densify these powders, in which case particle bonding occurs owing to thermal energy to create a solid structure, as is shown in the figures over here, where you have discrete particles and you begin to have atomic motion across the particles, and you begin to form these necks. You begin to eliminate some of the larger porosity and begin to create smaller voids. The atomic motion leads to bonding, which increases strength and also has a lot of other properties. Typical sintering phenomena include particles bond when heated. There's a loss of surface area, so you can characterize bond strength or surface area changes to follow the sintering behavior. There'll be the growth of necks. There'll be change of dimensions, as can be seen from this printed part to a densified part. Properties have to be improved: thermal conductivity, electrical conductivity, density, strength, so on. Here are the example of three different microstructures possible as examples after sintering. So you can see that you can have chemical homogenization, you can have grain growth, so microstructures coarsen, and basically you cannot go from here back to that. You cannot go from this dense region to back to the expanded porous region. It's irreversible. These are important to understand during to appreciate sintering phenomena. If you increase the temperature beyond the melting point, of course, you will have melt pools, and they have to solidify, and so a lot of phenomena that you end up having to characterize are more akin to either casting or more likely welding processes. Okay, so there are many different processing factors in sintering phenomena alone. Beyond that, for additive manufacturing, there are even more and even more factors. What is the driving force of sintering? Why do powders sinter? You have a curved surface over here. If you zoom into that curved surface, you will begin to see that the curvature causes strains. That strain also results in stored energy, surface energy. The atoms near the surface compared to the atoms in the bulk have no nearest neighbors, and so they have extra electron available for bonding. So they are in a higher energy state. And so high surface energy associated with the existence of this curved surface provides the driving force for atoms to move from the surface of one powder and begin to form a neck region and bonds between the atoms of another surface. A lot of 3D printing is based on layer by layer processes. So you end up having these thin regions. And so densification is a little bit more complicated under those conditions. Uh, These phenomena are beginning to get well studied in the traditional sintering arena, and now we have an opportunity to extend those to further our understanding for 3D printing phenomena. So to summarize, majority of metal additive manufacturing is dominated by the use of powders. In addition, you can use wires and sheet stock. Metal powders have many different attributes, including size distribution, shape, packing behavior, flow behavior, and so on. The variation of these metal powder attributes can affect how we create shapes by any process, and we have to appreciate them in the context of 3D printing and its in its many variants. What kind of process conditions can best consolidate the component? What happens to the properties that emerge out of that? Sintering is the common method by which powders are densified in traditional powder metallurgy. There are variations of using this phenomenon in 3D printing as well. In addition, you can raise the temperature above the melting point and then completely melt all the material. And that is another route for densification in the context of 3D printing processes. So in the next class, we are going to look at different kinds of metals that have been successfully processed by 3D printing. Important distinguishing features compared to other options that are available for traditional processing routes. This is going to be the focus of the next class.